In this video, I'm giving you an introduction to combustion. So let's jump into the topic with mathematical modeling minds. What is combustion? Combustion is the burning of a fuel in the form of either gas, liquid, or solid, where the fuel is oxidized, involving heat release and often light emission. When there is a rapid oxidation, both light and heat is emitted, and if the oxidation is slow, little heat is emitted with no light. So, what is a fuel? Fuel could be any substance that can be burned to produce energy to be used as heat or work. An oxidizer is a type of chemical which a fuel requires to burn. Air is the most used oxidizer. It is a mixture of oxygen and nitrogen with 21% of oxygen and 79% of nitrogen. But do you know how these rockets operate? In space, there is no atmosphere to provide oxygen or other oxidizers, so rockets need to carry up their own oxidizers. Usually, they are carried in a different tank than the fuel and released in the proper proportion with the fuel when the rocket is fired. Combustion can happen either in flame or non-flame mode. In flamed combustion, there is a thin reaction zone with intense chemical reaction propagating through the unburned fuel mixture. This thin zone is called a flame. Behind the flame, there are hot products of combustion. And the flames can be either premixed or non-premixed. In premixed flames, fuel and oxidizer is mixed at molecular level prior to any reaction. Spark ignition engine is an example of a premixed flame. Non-premixed flames are also called diffused flames. The fuel and the oxidizer are separated. The reaction only occurs at the interface between the fuel and the oxidizer. At the interface, both mixing and reaction takes place. For example, we can think of a burning candle. Do you know the use of stoichiometry in combustion? The stoichiometric quantity of oxidizer is just that the amount needed to completely burn a given quantity of fuel. Then it forms a stoichiometric mixture. In a lean mixture, oxidizer is supplied more than the stoichiometric quantity. And in a rich mixture, oxidizer is supplied less than the stoichiometric quantity. Let's have a look at a stoichiometric reaction. Consider the combustion of the hydrocarbon CxHy in air. For CxHy, the stoichiometric relation can be expressed using a simple atom balance. There are X atoms of carbon and Y atoms of hydrogen in both reactants and products. Air is represented by a mixture of 1 oxygen molecule and 3.76 molecules of nitrogen. And here I have shown you how to obtain those numbers for air. There are 21% of oxygen and 79% of nitrogen in air, which is a volume percentage, and it is equivalent to molar percentages. That means per 1 mole of oxygen, there are 3.76 moles of nitrogen. The stoichiometric quantity of air required for combustion of CxHy is A. We can find A by balancing the oxygen atoms, and it is equal to X plus Y divided by 4. Stoichiometric air to fuel ratio is given by the mass of air divided by mass of fuel. Mass of air is given by the total number of moles of air times molar mass of air. Mass of fuel is equal to 1 times molar mass of fuel. And we can take the molar mass of air as 28.85 gram per mole. Equivalence ratio is used to quantitatively indicate whether a fuel oxidizer mixture is rich, lean or stoichiometric. If the ratio is greater than 1, it is a rich mixture, less than 1, a lean mixture, and if the ratio is equal to 1, it is a stoichiometric mixture. These are some important terms used in combustion to calculate the percentage of stoichiometric air and the percentage of excess air. Let's have a look at an example. Assume a methane burner operating at an equivalence ratio of 0.3. If the air flow rate is 10 kilograms per second, what is the fuel flow rate and air to fuel ratio? We can first write the general stoichiometric equation for burning of a hydrocarbon. And then we can apply that for methane. So here we have x equal to 1 and y equals to 4. With x and y values, we can calculate A. With the A, we can write the stoichiometric equation for combustion of methane. Based on the equation, we can write the stoichiometric air to fuel ratio. So we calculate it as 17.1. And based on the equivalence ratio relation, we can find the air to fuel ratio for this specific process, which is equal to 57. And air to fuel ratio can also be written as mass flow rate of air divided by mass flow rate of fuel. So we are already provided with mass flow rate of air, which is equal to 10 kilograms per second. And then we can calculate mass flow rate of fuel as 0.17 kilograms per second. So here is the end of the Introduction to Combustion Part 1. Let's meet again in Combustion Part 2. Thank you.